Welcome back. We are progressing through motor control systems. So far, if you haven't kind of picked up yet, we are building a motor control system. We started out with our three-phase system, with our three phases of voltage coming into a disconnect, our circuit protection for short circuits, and also for overload protection, and also our motor controller. We did all that. What we're doing is we're making our way toward a basic control system. Okay, we talked about the power or the motor circuit. Now we're going to be moving toward the control circuit, but before we do that, we've got to cover an area in between, and that is the transformer that steps up the high voltage from our power circuit down to a lower, safer control circuit. Okay, so this lecture is going to be on control transformers. Now, first of all, there are a ton of different types of transformers. We're going to get to control transformers in just a minute, but I just thought I'd talk about some of the other types of transformers and how they fit into the entire system before that makes it down to into our plants or into our lab or wherever we're working. Okay, so most of you have seen a step-down transformer. It's like this one right here. They're up on the utility poles. They take the high voltage and they step it down to a lower voltage that comes into our homes or our businesses. Okay. Also, now with a lot of municipalities putting their utilities underground, okay, they're doing away with the telephone, with the utility poles and some of these transformers overhead, and now we're starting to see these on ground level. But it's still a transformer, works the exact same way. Okay, and this example here I've got on the screen here. So, probably one you've got in your home. Okay, it's a step-down transformer that's either used in your HVAC for your heating and air. Okay, because your heating and air has 240 volts, and the voltage behind the thermostat on your wall is not 240 volts. It's probably about 24 or maybe even 12 volts. Sometimes in some cases it's 5 volts. So it's a step-down transformer used for that purpose. And also, if you got a doorbell, you've got a step-down transformer that takes 120 volts and steps it down to about 12 or 14 volts that runs your doorbell, because it's a safer voltage for someone standing outside in the wet and the rain. When they go to press that plastic button on your front door to make your doorbell ring, you're going to have a much smaller, safer voltage there behind that doorbell. Okay. Now, this is another type of massive kind I've worked with before in the aluminum industry. One of the things that transformers do is they generate a lot of heat. Okay, and this massive transformer actually requires oil be circulated through the transformer by the coils to pull the heat off. The oil is circulated through a heat exchanger and pumped back into it to help cool off the transformer. This is a massive thing, but anyway, it's just all shapes and sizes. Now here's kind of the cool thing about transformers. They basically all have three parts that are in common. Okay, we're going to get into them, but there are no moving parts and there's no electrical connections from one side to the other. And I think that's what's one of the coolest things about transformers. Okay. So we're going to talk about three types. We've got the step up that increases our input voltage to a higher level. We're going to have the step down that does just the exact opposite. It takes our input voltage and steps it down to a lower level. And then we have an isolation transformer that takes our input voltage and doesn't change it at all. I'll just speak briefly on this one. The reason we have isolation transformers is because sometimes power coming in is dirty, it's got spikes, okay, and some fluctuations. And an isolation transformer, you'll see how they operate a little bit later. You'll see that the transformer will buffer out those spikes and clean the power up. So a lot of times, particularly when there are PLCs, robotics, process control, things that are very susceptible to spikes and things like that, we want clean power going into those systems. So we always use an isolation transformer that doesn't raise or lower the incoming voltage. Okay. So I like to look at things from a systemic or a holistic view. So first thing we're going to do when we come out of the power plant. Again, our power plant's up there at Seabury, Big Rivers. We have TVA in Western Kentucky, Paradise, and over there by the land between the lakes, excuse me, for the hydropower. Anyway, they're producing the power, and the first thing they're going to do is they're going to step the power up. And the reason we're going to do that is we're going to transfer it or transmit it across long distances from the power plant, the generation station. So the first thing we do is we step up that voltage, okay, up to levels from about 13.8 or 13,800 up to, 138,000 up to 500,000 volts, okay? Quite a bit of a voltage there. So why do we want to do that? Well, before we can get into that, we need to back up and look at Ohm's Law. You should be familiar with this by now. Ohm's Law is that George Ohms was a scientist, mathematician that showed us that there was a mathematical relationship between the voltage, the current, and the resistance in a circuit. Okay, and his basically what he came up with is that if you divide your voltage by your current, you're going to get your resistance. Likewise, if you divide your voltage by your resistance, you'll get your current value. Or if you don't know what your voltage is, but you know your current and your resistance, you can multiply these two and you can get your voltage. Okay, that's the mathematical relationship of Ohm's law. But we've got to take it a little bit further, and we're going we're going to look at Watt's law. Now, a lot of you hear the word watts. Watts is basically a unit of measure for measuring power. Okay, and the voltage and the current are inversely proportional. So if we've got our power up here, kind of like the same T with Ohm's law, if we've got our power here, these two multiplied are our power. Okay. Now, if one goes up, the other goes down. So they're inversely proportional. That's going to be critical. Okay. Let me give you an example. Okay. Everybody's got one of these probably in their home or something like it. Okay. It's a blow dryer. All right. And most blow dryers are about 1,250 to 1,500 watts. Again, watts is our unit of measure for power. All right. So it's about 1,500 watts. Okay. So we're going to look at this mathematically. We have 1,500 watts. Well, our homes are run and powered with 120 volts. Okay. So we can do the math and divide 1,500 by 120, and we wound up pulling 12.5 amps for a 1,500 watt blow dryer. Okay. Now, to show you the inversely proportional part, suppose we put 240 volts into our blow dryer. Okay, still 1,500 watts, but suppose we put 240 volts in here, and I do not recommend you doing this at home. So don't be plugging 240 volts into your blow dryer. But if you do, if you were able to do that, our voltage went up, so our current is going to come down proportionally. Okay. So we will be, instead of pulling 12.5 amps, we're now going to pull 6 1/4, okay, 6.25 amps. So the power doesn't ever change. Power consumption does not change, okay, but the voltage and the current can be inversely proportional, okay. Another example is I've got a 1949 Craftsman table saw that I got and restored it, and it's got a little motor, a dual voltage motor out here, and when I first put it together and rebuilt it, it started tripping circuit breakers. About every third or fourth time I'd go to start it to use it, it would trip circuit breaker. Well, as you remember from the lesson previously, we talked about inrush current. And what was happening was the inrush current was spiking, it was tripping my circuit breaker in my breaker panel. Well, because it was a dual voltage motor, and that was on 120 volts, by the way, because it was a dual voltage motor, I was able to wire the motor, change the terminals around, and make it a 240 volt motor. So I plugged it into a 240 volt breaker, or connected it through a 240 volt breaker, and my inrush current went down proportionally. It cut it in half. So instead of my 15 amp circuit breaker tripping at 120 volts, I got a 15 amp dual pole or double pole breaker, and I was able to drop the inrush current by half. So now I have no tripping problems when ever I start the saw. That's great. Okay, fantastic saw. But that was just a kind of an example of the inversely proportional concept I was talking to you when we were talking about power. Okay. All right. So what we've done is we are going to step that up. Now remember, we've jacked that voltage up really high. Okay. So what's going to happen with our current? It's going to start to drop. That's a good thing because we're going to be transmitting this over long distances. Okay, you look down the road and you see these utility towers with 3 phases of voltage going down the parkways, down the highways, interstates, and cutting across fields, big wide swaths cut through these fields to accommodate these towers. Okay, well, what we've done, we've jacked that voltage way up and our current has come down. The advantage of that is saving some money for the utility companies. Okay, instead of having to run a massive conductor as a result of having lower voltage, the higher the voltage they go up, the less current they have to pull. So they can put smaller conductors across their transmission lines going, long distances. Now, once we get down to where we want to do, where we're going to utilize that power, okay, and again, we're talking about power going through these lines, okay, not just voltage, not just current, but power, okay. We're going to step the voltage down, okay. Now that's kind of where we get into control transformers. I want to move into that. There's a couple examples right here of control transformers. They come in all different shapes and sizes. It just depends on their application and things like that. But the purpose of a control transformer is to step down the voltages to lower, safer levels, particularly when there is human interaction going on around the control circuit. Okay, I would much rather get shocked by 24 volts than 277, 240, or 480. So that's why we step those voltages, those higher voltages down, because we usually have some type of interaction with the machine behind, with control, with push buttons and switches and things like that, devices like that. And I would much rather have a smaller voltage. It's just a lot safer. Okay. As usual, we go over the control transformer symbol. This is the symbol for a control transformer. It's actually the symbol for a step-down control transformer. We have more windings on the primary side than the secondary side. Okay, we're going to get into all that here just momentarily, so don't worry about it too much. But you will need to know how to draw this, okay? Because we are going to start designing circuits very soon. All right. So you remember I said that regardless of whether it's the doorbell transformer or that massive transformer that we used in primary aluminum, they all have three basic components. Some are more a little technologically advanced than others as far as being able to monitor and things like that. But a transformer, they all do the same thing, and they all do it with the three basic parts. Okay, the first one is the primary coil, the second one is the secondary coil, and the third one is the core. Now the core can vary a little bit. It can be iron, it can be air, a lot of different variations. For our purposes in control transformers, we will be using an iron core, okay? And here's just a cutaway, and when I'm talking about an iron core, these are laminated sheets of iron stacked on top of each other. And I'll go ahead and tell you, the reason we use this laminated core is because the saturation of the magnetic field is much better as opposed to being one giant chunk of steel or chunk of iron, okay? So they laminate it, okay? And if you've done the three-phase induction motor lab, you remember they used laminated discs in the rotor because that's for better magnetic field saturation within the rotor. Okay, and you got the primary windings that are wrapped around the core and the secondary windings that are wrapped around the core as well. Okay, just a quick cutaway. We're going to get into all this now. Here's how it works. Okay, we have, when I'm talking about a coil, okay, we said we had a primary and a secondary coil. But remember, if you've seen me in the lab, you've worked with me at all in the lab in your classes, I've told you a gazillion times, a coil is nothing more than one piece of wire wrapped around and around in a circle, okay? Same thing right here, one piece of wire beginning and end wrapped around this iron core, okay? We are wrapping it around a piece of that laminated iron, okay? So we apply an alternating current. Now that's critical, pay attention to that part. We apply an alternating current to this transformer, and I'm going to show you why, okay? First of all, the alternating current between the negative and the positive, remember the AC sine wave here, we're going through a cycle of, we are peaking positive, going through our zero plane, peaking negative, back to our zero plane. That's one cycle. We're doing that 60 times a second here in the United States. If you remember from our previous lesson, that was hertz, okay? So we are applying 60 hertz of voltage to our primary coil. Now what that does is, first of all, it sets up a magnetic field in the iron core, okay? If you take a piece of wire and wrap it around a nail and hook it to a DC battery or an AC voltage, either one of those is going to create a magnet, okay? You can pick little things up like a paper clip or something like that. We used to do that in elementary school as science experiments and stuff. But what we do is we apply an alternating current to our primary coil, and that sets up a magnetic field. And because it's alternating, the magnetic field is changing directions 60 times a second. Okay, so this is the arrows here representing. I don't have any arrows representing the reversing, but it reverses direction 60 times a second. Okay. Now that phenomenon of building and collapsing a magnetic field, because remember we're building a magnetic field here with the peak of our voltage, and then we're collapsing it when we go to our zero plane, okay, and there's no magnetic field at this point, so then we got a negative sine wave here, and we're building again in the negative direction, so it's going one direction, collapsing, going in the other direction, collapsing, and doing this 60 times a second. So that building and collapsing of that magnetic field in our iron core sets up a magnetic field that's reversing direction 60 times a second, okay? Now, what happens next is that magnetic field is reversing 60 times a second in this iron core. So what we've done is we've wrapped another coil of wire, again, one piece of wire, wrapped it around there. This time we've not wrapped it as many times. We've not gone around it as many times, fewer turns on the secondary side. And with that magnetic field reversing direction 60 times a second inside that coil, okay? Inside that coil, you know, it's back and forth like this. That induces a voltage in the secondary, okay? Pay attention to this part here. We're inducing a magnetic field into this, with this coil, and that's one induction. And then we're inducing a voltage out of the secondary, okay? So you got two inductions going on at the same time. It's mutual induction. That's where we get the term mutual induction, okay? So we've induced a magnetic field here with alternating current, and we are inducing a voltage. As a result of that, we're inducing a voltage at the secondary that we can use, okay? So we put a higher voltage here with more windings on this side. We've stepped it down with fewer windings. We've got a smaller, slower, safer voltage here, okay? So what we wind up with is a small circuit here that we, again, are applying the voltage, and our current is reversing, and we're passing that through this coil of wire, and now we've put a load on here, and we've got a small, we're lighting up a small light bulb, okay? And that's basically how the transformer works. Now, the reason I'll talk to you about the AC part, why that's so important, you could put DC voltage on a transformer, but number one, it's going to burn it up in a heartbeat, okay? But the reason being is because you're completely saturating that magnetic field with no zero plane at all, okay? So it's going to burn that up. The other thing is you will not get a secondary voltage out of your secondary windings because you don't have that building and collapsing. You're going to have a heck of a magnet with DC. Don't get me wrong, have a heck of a magnet. But what you're not going to have is that alternating current building and collapsing, reversing your directions back and forth, building and collapsing inside this coil that's inducing the voltage. And without that, you're not going to have any voltage coming out of the secondary. You won't have any light or anything like that. So yeah, you can put DC voltage on there and you can watch it just kind of smoke in a heartbeat. But that's why we have to have that AC alternating current. That is what causes us to have a voltage on the second side, okay? All right, so this is the cool part that I've always kind of thought was kind of cool about transformers, is now notice that we never wired the primary side to the secondary, okay? All we've done is take a piece of wire and wrapped it around and around and around this piece of iron, okay? And we've done the same thing over here. We've never tied these two coils together electrically or mechanically, okay? We've never tied this coil, we never wired it to the core. You know, we never wired this one to the core either, okay? So they're completely independent. So the voltage transfers from this side to the other through that mutual induction. Again, we're not making connections to get it done, just except for, you know, hooking the power to the coil over here, and we put a load on here like you saw the light bulb, but there is no connection between the two, all right? So that's critical for you to remember, all right? So on a step-up transformer, okay, that's the opposite of what we were looking at previously. With a step-up, you're going to have fewer turns on your primary side, and you're going to have more turns on your secondary side. Just the opposite with the with the step down. Okay. Again, with the step down, we got more turns on the primary side and fewer turns on the secondary side. Okay. And with an isolation transformer, we got 1-to-1. Be the same number of turns on both sides. We're not going to really get into that much with isolation transformers in this class. Okay. So we have our drawing. This is our system here, okay? We're taking our voltage and we're putting it into the primary side. This is where it all starts. We've got to put power onto the primary side of the transformer, okay? And then we get it through our secondary coil, okay? This is our iron core in our drawing or our symbol. That's the iron core there. And this is the fewer turns on the secondary. And our secondary side of our transformer is always designated X1 and X2. Kind of important for you to know that, all right? So again, we've got you should know what this is. These are our connection points, okay? This is not a connection point. We're going through our fuses because we're going to protect the coil in case we had a short circuit of some sort, but we have that's our symbol inside of our drawing, okay? All right, so All right, now transformers are rated in two different ways: kilovolt amps or volt amps. They're basically the same. It's just one is to the thousandths and the other is not. Okay, we can figure out how what the volt amps are on a transformer just simply by multiplying the volts times the amps. That's how you get volt amps. Okay, so for example, if we have a transformer that is our primary is going to run on 480 volts, and we have 10 amps. Okay, so we're going to need a 4800 volt amp transformer. There's a little bit more to calculating the sizing of transformers than that, but in general terms, volts times amps gives us 4800 volt amps. Okay, now I said it was rated also in kilovolt amps. Well, all we've got to do is move our decimal place 3 times to the left, 2, 3, to it's right between the 4 and the 8, becomes 4.8 kilovolt amps. Okay. Now, using another mathematical example, it's not too hard. You have 240 volts of power and 25 amp load. Okay, what will be your volt amp? Simply multiply volts times your amperage, and you'll have 6,000 volt amps. Okay, and this is wrong. This should be 6. So if I move my decimal 3 places to the left, I wind up with 6 kilovolt amps, not 0.6, but 6 kilovolt amps. All right. So that's how we calculate it. And remember, we said that it's a lot like that blow dryer we were looking at. 1500 watts is 1500 watts, okay? It never changes. Well, same thing with a transformer, okay? If we have a 6,000 volt amp transformer, okay, that's 6,000 volt amps on either side, okay? Whether it's the primary or secondary. That does not get affected by the step up or the step down, okay? So I've got a 6,000 volt amp, and I'm putting 480 volts into my primary circuit right here. I can take 2 of those phases in our drawing we saw a minute ago, and I apply it right here. Just hook it up there, create that magnetic field. All right, 480 volts. Then I'm going to have 12.5 amps on the primary side. Okay. Well, remember, nothing changes with a 6,000 volts amp. It's still a 6,000 or 6 kVA transformer regardless. So now we're on the secondary side. Okay. And let's say this is a 4-to-1 transformer, okay? 480 volts, okay, stepping it down by 4 gives us 120 volts on the secondary side. I'm going to show you the math behind that in a couple more slides. But now instead of 480 volts, we're producing 120 volts. Well, remember, voltage and current are inversely proportional, okay? So I can't drop my voltage and the amperage stay the same. No, the amperage is going to go up by 4 proportionally, okay? So 6,000 volt amps divided by 120. Now my secondary side is going to need to be rated for 50 amps. Okay, so regardless of the side, it's all a 6,000 volt amp or 6 kVA transformer. Okay, now the difference will be the voltage, and that will determine the current that's pulled on that side. All right. So same thing, another mathematical. Just going through the math real quick. We got a 2,400 volt or 2.4 volt amp. Kilovolt amp transformer. We apply 240 volts. Okay, our amperage is going to be 10. Yep. And then we have still a 2,400 volt amp or 2.4 kilovolt amp transformer. Now we have it's a 2-to-1, so instead of 240 volts, we get 120 volts out by half. Okay, and then since this went down by half, this is going to double. Okay, inversely proportional. All right. So now. Let me ask you a question here. Think about this for a second. If you know that this is a higher voltage and a lower amp, and this is a lower voltage and higher amp, which side's going to have the heavier wire? Which one's going to have the heavier conductor? Well, I can tell you, it's going to be the secondary side, because it's going to be higher current being pulled on the secondary side. That's when you're going down the road. That's why they have that smaller current, or excuse me, that smaller conductor on those long transmission lines, okay? When it gets to your home or your business, the lines coming off of the secondary side of that transformer on the pole or down on the ground, whatever it is, are much bigger than the ones that have been traveling down the road, okay? Because they are stepping the voltage down right before it goes into your home or your business, okay? Turns ratio, okay? This is the difference between the number of turns on the primary and the secondary, okay? And if you figure this out mathematically, okay? The turns ratio is the number of turns of the primary divided by the number of turns on the secondary. Okay, so if I had, we'll just use round numbers. I don't have it on the screen or anything. But if I had if I have 1,000 turns on my primary side and I had 250 on my secondary, I divide 1,000 by 250, gives us a 4, and that's a 4-to-1 transformer, okay? Or 4-to-1 turns ratio between the primary and secondary. You can then take that information and determine what your output voltage on the secondary is going to be. If you know that you've got 480 volts going in, and we've got a 4-to-1 transformer, you divide that voltage of the primary by the secondary, okay? That's 4, and that'll be 4-to-1. So you divide your voltage of the primary by 4, 480 divided by 4, and the voltage coming out on the secondary is going to be 120 volts, okay? So here's how you write it mathematically. N represents the number of turns. Your subscript is the P for primary, or your subscript of S is for the secondary. So number of turns on your primary divided by the number of turns on your secondary. It's the same thing as the voltage by the primary being divided by the voltage of the secondary, okay? Also, if you only know, for example, if you know you have voltage on the primary of say 120 volts, but you don't know what your primary voltage is going to be, but you know it on the secondary, you can turn it around and multiply it. So if you have 120 volts on this side, we got a 4-to-1 ratio, multiply the secondary by the ratio, which is 4, and you wind up with the number of the voltage on the secondary, okay? So mathematically, you can figure it all out. Again, you've got a lot of different types of transformers. The ones that we're going to stay focused on is this one right here. This is the step-down transformer. And now that we've talked about that, you can kind of see in the symbol, you've got more turns on your primary side than you do on your secondary. Makes it a step-down transformer, okay? With an iron core in the middle. Just to show you a different one, this is a step-up transformer with fewer turns on the primary side than on the secondary, so it's a step up, okay? Now, a transformer can also have multiple primary coils and multiple secondary coils. It makes it a much more versatile transformer. You don't have to carry as many in your store's shelf. So they do come configurable with multiple primaries and multiple secondaries. Okay, I'm going to show you that here in just a second. For example, okay, we're going to use 480 volts as our high voltage and 240 volts as our low voltage. Okay, so if I've got a low voltage primary coming in, our goal here is to have 120 volts coming out of the secondary. Okay, so we've got to maintain that ratio. We've got to keep that ratio between our voltages correct. Okay, so if we've got 240 volts, what we want to do is we want to put these two coils. This particular transformer has two independent coils on the primary side. We want to put those coils in parallel. Okay, and what they're doing here is, you'll see this black dot. Well, the black dot, remember from lesson 1 and also lesson 2, that's a connection point. You got a small piece of connector right here between the two. It's a jumper wire. Okay, so you're going to jump a wire between 1 and 3, and then you're going to also put a jumper wire between 2 and 4. So it basically takes us into H1. Okay, and then we're going to jumper it over between 2 and 4. Okay, so our power is going to come from here to here and to right here and here. All right, these are going to be our neutrals. All right, and they're going to be tied in series. Okay, for a higher voltage, if we go 480 volts, we are going to tie H2 and H3, these right here, together, so that when we put voltage in there, we have to add turns on our primary because we've jacked our voltage up. So we're going to have to put more coils in there. So what we're going to do is we're going to come power into H1, go to H2. We're jumping between 2 and 3, okay, and then we continue on. So basically, that has put these coils, these turns, in series with one another. Okay, so we've increased the resistive load of our transformer. Okay, so we have a higher voltage, we've got to go with in series. We have a lower voltage, we're going to go with in parallel. So H1 and H3. Okay, this is the incoming side of each coil. Okay, going to each side of the coil. Okay, H1 and H3 will be tied to one leg of our power. H2 and H4. Okay, that's the outcoming side of this coil, the outcoming side of this coil. They're going to be tied together, so our power is going to go in here, and we're going to have the other leg coming into H2 and 4. That puts them in series. Our goal is, regardless of the two voltages, whichever voltage we have on the primary side, we've got to maintain 120 volts coming out of it. Okay, so this is one of the this is a schematic of the one that you'll be working with in the lab. You can see you can configure it for 200, 480, or 480 on the primary side, and 120 or 240. Depends on where you put your jumpers, okay? So that'll make a big difference on what your output voltage is. So they're configurable. That's my point, is that they are configurable on our transformers, okay? I just kind of threw this one up here. Some of you guys might be car guys. I've got a 63 Mercury. We rebuilt it, and it belonged to my wife's dad. And we, I kept everything original except for the ignition system. I put electronic ignition in there to make it a little more reliable and easy to start. But basically, remember I said, this is the interesting thing here. I said you can't use DC for a transformer. Now that's true, but on a car you got DC voltage as your power source. Okay, so how do we turn this into a transformer if you can only have AC? Well, what happens is you turn your ignition switch on and you power up the primary side of your transformer. Now, this is a step-up transformer, okay? Because what we're doing is we're taking 12 volts from our battery, and we got to get somewhere around 15,000 volts to our spark plug, okay? So that we can fire the fuel and ignite the fuel while it's under compression, okay? And while it's flooded with gasoline. So we got to have a good hot spark. 12 volts is not going to cut it, so we got to step it up. So what we do, we close our ignition switch, and notice we've got fewer turns on the primary and a lot more on the secondary. So we've got a little iron core in the middle going on. Okay, so we turn the switch on, and we create a magnetic field. It saturates this coil right here. When we turn our switch over to start the starter motor, and our cams under our distributor start to open and close points, what happens is we allow that, we open the circuit and we stop building the magnetic field in this coil. This coil will then release. It will collapse and send the spark over to the spark plug. And it'll do it for every cylinder. But what we're doing is we're making and breaking and opening and closing and saturating and collapsing, building and collapsing by opening and closing the primary circuit. Okay? Just thought it's kind of interesting. It's nothing to do with our motor controls class, but didn't know if some of you might know this, knew that, but your lawnmowers have coils just like that too. Okay? But now I want to move into troubleshooting the transformers. Okay? Step number one, before you determine whether your transformer is good or bad, first of all, make sure you got power going to it. Okay? Transformer's not going to work without it. Okay? Transformer doesn't create power, it transforms it. So it transforms it. So you've got to have power going into it. So the first thing you do is you can check the secondary side with your voltmeter. Do that. You're safe doing that. Check and see if you got it. And then come over here and check and see if you got voltage going into it. A lot of times students will say, got no voltage, it's got to be the windings on the secondary is bad. Well, no, not necessarily. Or they'll say, well, the windings got to be bad on the primary side. No, not necessarily. Find out if you got voltage first, okay? I've seen voltage go out a lot more than I have transformers. Now, transformers do fail, but check, make sure you got voltage. That's the first thing you want to do, okay? You want to check and make sure you got it coming out of the secondary, okay? Now, if you don't have power going in, if you have power going in and you're not getting anything coming out, okay, then isolate the transformer, take the power completely off of it, okay? And then let's start using our ohm meter, and let's check the resistance of our coils, okay? We want to, depending on whether it's in parallel or series, what we're trying to do is make sure that these coils are not burned in two, which would be an open, or they're not short-circuited. Now, with the coil of a transformer, okay, this looks like bare copper wire, but it's actually transformer wire. It's a solid wire with a varnish or coating on it for insulation. All right, and so what we've got is these coils will wrap around like this, and after a while, there's a lot of vibration going on and heat, and it'll break that insulation down. And instead of the voltage going into the beginning of the wire and the coil and all the way out and coming out the other end, we'll wind up with a short, okay, where it overlaps and has made contact. Okay, we don't want that to happen. So one way that a transformer can fail is it can burn open, completely just burn a gap in between the windings, or it can short. Okay, it can happen on the primary side, it can happen on the secondary side. So we want to check our windings with both sides with our ohm meter. Okay, and the other thing, the other way it can fail is that we could have continuity between these two coils. Okay, that's something that we don't want to happen, because They are separated, a lot of times they're separated with a paper insulation, okay? And if that insulation were to degrade to the point where it is no longer separating the two, and again, the vibration of the transformer and the heat and everything going on in there, again, their insulation can abrade between the primary and the secondary. You could have a short between these two. You do not want any type of continuity between your primary and your secondary. So if you got your meter, take your meter here on one end of your primary, check it to your secondary. Should not have anything at all, okay? And likewise, you should not have any type of continuity between your coils and your core, okay? If, again, the coils are wrapped around that iron core, and with vibration and everything, it could possibly short to the iron core. So, let's see if I can get a picture here. Okay, so what we would have here would be check our meter and literally put it on the iron core, the outside of the iron core, making sure you got a good contact, a good connection, to make sure that the primary and the secondary are not touching that iron core. Those are the three ways they can fail. They can short. One of the coils can short out. One of the coils can burn open, or the coils could possibly come in contact with the iron core, and that's the way they fail. Okay, so you'll get into that as you come to the lab. So this is pretty much control transformers. I wanted to give you a broad look and start narrowing it down to the control part, but I hope it's been helpful. If you've got any questions, particularly while you're in the lab, come see me. Also, you're going to be working with a homemade transformer. It really breaks this down, makes it a lot more simple to understand. But really, there's no moving parts. There's three basic parts to them. It's pretty cool. So if you've got any questions, let me know. Hope you enjoyed the lecture. Hope you got something out of it. Hope you've been taking notes too. So I guess we'll see you in the lab. Thanks.